inferences and counting. It could be, well, it's on the Cambridge University website. There is abstract if you would like to check. So it could be interesting for a few people here. So we decided to move Vinogradov's talks for today. Okay.
So
11:30 tomorrow. Or Vinogradov today 2:30. Yes.
So first of all, let me thank the organizer because it's a real pleasure to be here. And okay, so this is joint work with Sébastien Grisel. And Frédéric Maucourant.
Which accent is that?
What?
Which accent is that? Is it flat?
No, it's not flat. It's this way. Okay. So the goal of the talk is to give some description of our relationships between four quantities, which are the entropy, the drift, the exponential volume growth rate, and the spectral radius. So, okay. First, the setup. So I have gamma, a countable group. And you can think it of exponential growth. Otherwise, what I'm saying what? Oh, I defined it. I'll take half of the seminar to define these quantities and to explain a little bit what they represent, so geometrically. So we take D a distance, and you ask that D is gamma invariant on the left, and also that to be proper. And I define, so I'll simply write norm of gamma to be the distance to the identity. So you can really think it's a well distance given for a finitely generated. Okay. So there is a first number which is V. This is the limit in as n tends to infinity of the logarithm of the size of a ball around the identity of radius n. So it's the exponential growth rate. Okay. And we'll try to keep track of a very important example here, which is a big free group on K generators. So D would be the world metric with respect to A1, AK. And so volume group here is, let me see, log of 2K minus 1. Okay. So now we want to do some random walks here. So let mu be a probability m, and I will ask three conditions such that, and so the first one is the most important, mu is symmetric. Which is mu of gamma, mu of gamma. Okay. And I insist because most of the thing I will say later will be obviously false if you measure symmetric. So, the second is that it has finite second moment, so that n2 of mu, which is the integral of gamma squared minus gamma. It's a finite, it's a standable sum, if you prefer. Like this. 1/2. I want it to be finite. And the third hypothesis, which is not really an hypothesis, it's you assume that the support of mu generates gamma, otherwise you just change gamma to be the support, group generated support. And in our favorite example, you take mu equals sum of the Dirac masons and AI plus or minus 1. And so, picture. So our measure is 1,4,1,4,1,4,4. So I'll try to explain now the H, L, and rho. So you have associated quantities. And first, so you look at x1, xn, random variables, or flow mu. And you want to look at the random walk, so write Zn to be the product x1, xn. It's as low mu in n time. And first definition theorem is that you have a drift, which is the limit as n to infinity of the size of Zn over n, almost 0. Okay, for almost any one walk, the distance to the origin grows linearly. Okay, so on our example, what you see is at each time you choose a neighbor between 2k neighbors, and there is one of them that brings you back, and the others add something, add 1 to the distance. So the drift here, it's, so what I'm saying is that simply it's one of the cases. Okay. Secondly, I'll try to explain the spectral radius. So you look at the regular representation of gamma in the unitary of L2 of gamma. So this gives rise to an operator P reg of mu, which is simply the integral of the gamma pi of gamma mu of gamma, which is obviously an operator of norm less than 1. And the spectral radius, just its norm definition. Well, we got a norm of mu. And so this one is self-adjoint, so its spectral radius is equal to its norm. So okay. And so this is a quantity that is always in 0 and 1. And there's a theorem of Keston which says that gamma is amenable if and only if there is a spectral gap. Spectral radius is strictly.
Gamma is non-amino.
What?
Gamma is non-amino.
Thanks. Okay. And so here you can compute rho, which is in this case square root of 2k minus 1 over k. Okay. And there is also a very nice geometric interpretation of this rho, which is the following. So I think it's still a theorem of Keston. But if you look at the probability of return to the origin at time n, and typically it will have exponential decay. And so you have to take 1 over n to have a quantity, and then it can happen. For example, for this walk, you can come back in an odd number stem to the identity, so you have to somehow forget some. So you take the Lenisouk. 1 times to infinity of this, and then you find the spectral radius. So and now maybe the quantity that is the hardest to grasp, to have a grasp on, is the entropy. So as you know, the entropy of a measure is simply sum of gamma minus log u of gamma times u of gamma. And the entropy of a random walk is simply the limit n tends to infinity. The h of star n over n. Okay, so this is a number which is bigger than 0. It can be infinite if you only choose your margin u. Okay. So there is a nice geometric characterization the following. You look at the probability that you are in the point theory. In other terms, if you take the two different random walks, maybe they would join at time n, and that's the exponential decay of this probability. So, which must be missing a log in minus log in 2h. Almost sure. So what does it mean? It means that you can understand, you can think of the n step of your random walk. This measure, you can think of it, is approximately a sum of exponential minus hn points, Dirac mass of weight exponential minus h. And so this is due to chi9 of h and h. Okay. So in our example, the h is equal to Here it's a nice example because it is equal to L times B. So it's 1 minus 1 of k times log of 2k. Okay.
Sorry, could you just I'm a bit confused. What is mu star n of Zn? Maybe can you just write that as a integral of something like?
What is it?
What does it really mean?
It means you take two different framework and you're looking at the probability that at time n they are at the same point.
Okay, but so this is just, but then the point is it's your average over all the points, right? It's a sum over all the.
No, it means for almost every trajectory, you fix a trajectory Zn. If it is typical, at each time, the probability of being where it is approximately exponential minus HA. So H is a diffusion factor somehow. So we have defined four numbers, and there are relationship between them. So let's talk about this. So first there is a theorem.
So it's almost every in your statement is about the measures and the trajectories on the endpoint, on the boundary.
Yeah. On the?
So this almost every.
Almost every. It's the whole
measure
trajectory. So you have a measure on all the set of all trajectories for a set of full measures. Because obviously you have trajectories for which this isn't true. If you just keep.
What I'm saying is that this almost surely
refers to the ZN.
Refers to a measure on the boundary, which is mu station.
No, it's simply the measure on the space of trajectories is just gamma to the n equal with mu n. Yeah, for this measure. So there's a theorem of Guizard. Which is say that the entropy is always smaller than L times V. And the proof is if you understand the geometric interpretation again, it's quite simple because at time n, mu n consists of that many points, and which are typical, and these points are at distance L times n. So if you're looking at how many points there are at distance L times n, then there you have the exponential bound. It's approximately exponential v times L n. That is the number of points which are at distance Ln. So these points must fit into these points. So the exponent h must be smaller than v times L. Maybe short proof waving hands, but basically it's the argument. Okay. So this means that you can, if the growth finite and n equals 0, then if the drift is 0, then the entropy must be 0, and if you have sub-exponential growth, you don't have any entropy. Okay, and in fact, we'll say shortly that if the spectral radius is less than 1, then both the entropy and the drift, there must be entropy and drift, and also that if you have so if you have So this one is an equivalence. And in our example, as I said, this inequality is an equality. So, and basically, one expects that it's almost the only case where it happens. But, okay, so now I renormalize the distance so that the M2, the second moment is equal to 1. And how do I do that? I just put, if I do that, I get a statement about the following quantities. So the drift is divided by the homothecy we have applied, and the volume growth is multiplied by second moment. Okay. And so L tilde is always between 0 and 1. So theorem is the following. You have two, right. H is bigger than this quantity, which depends on rho. And H is bigger than this quantity, which depends on the drift. Okay, so about the behavior, it behaves as we can expect, but if rho tends to 0, then H tends to infinity, and if L tilde tends to 1, then H tends to infinity. So one improves result of Hades, 73, which states that minus 2 log rho smaller than H, and moderately in the 80s, 90s, which say that 4 1 minus rho smaller than H. So this two equated. So this one captures essentially the same behavior at infinity, and this one captures the same behavior near 0. No, it's the contrary. When rho is so this one is not very good when rho tends to 0. This one is very good when rho tends to 0. Both functions are behind. Okay. And 2 improves the statement that I won't give because they do not renormalize by second moments like we do, but it improves results of Karn, Leyu, Matthews, and maybe there's two S. Yeah. And what's interesting is that it gives you some bounds which are purely geometric for these quantities. Corollary is that the L tilde is smaller than hyperbolic tangent of this 22. The entropy is smaller than the tilde hyperbolic tangent of the tilde H. and rho is bigger than 1 over cos h of this tilde of h. That means that if your group is not big enough, the drift cannot go as fast as you want. The entropy is bounded, and to have a really big spectral gap, you have to have a really big group. And there's an equality.
Sorry, is this a formal consequence of that?
Yeah, it's formal consequence of this and of this. Yeah, it's completely just, you read it, it works. Oh, nothing fancy. Okay, so what I didn't say is that both of these inequalities are, in fact, equalities in this case. And so we tried a little bit to characterize the group for which you have equalities here, and let's give you the following proposition. So assume gamma is hyperbolic and non-virtually free, and we assume, so usual assumption that a nu, and that mu has finite supports. Then 1, 2 are strict inequalities. Okay. So that's the results. So now I'll speak a little bit about the proof, which involve, in fact, only analysis on boundaries. Yeah.
The distance that you took in the beginning, it's not necessarily a work metric, is it?
No. I want it to be proper and to be invariant, left invariant.
And when gamma is virtually free?
When gamma is virtually free, it depends on the mu you
Exactly,
take.
the view.
What I don't know, if you take a virtually free, does there exist a random walk for which there are equalities? That I don't know. If you take a free group, obviously it works. If you take products of free products of z over 2, and so on.
But for the free group, you know that the only mu which gives equality is
I don't remember. I think so, but I'm not sure. Sorry, I don't remember. Yeah. Okay, so boundaries improve on the match. Okay. So first, let me, so all what we say will take place in some kind of abstract setting, which is so a gamma space B mu, gamma probability space, is called boundary if mu contributed with nu is equal to nu. That is, nu is stationary. Okay. When you have such boundary, so it can be, for instance, direct measure. It can be, in the following it will be the Boltzmann boundary or the Poisson boundary. So, when you have such a gamma space, it's a formal consequence of this that the mu is automatically quasi-invariant to the gamma. And so you can define the random decoding cocycle. Which is simply C of gamma psi is equal to derivative of gamma minus 1 and d mu and psi. Okay, and what we will do in the next is that we won't take some natural measure and so on gamma times d, you have the measure mu times nu, which is somehow natural. But what we will take is that we'll take the following measure. dm is 1 over c 1 half, 1 half, yeah. No, there's no 1 half. D mu d. And I don't really know why, but for this problem, it's a good measure to consider. And what we wanted to express the quantities, the entropy, the drift, and the spectral radius as some kind of integral of this space endowed with this measure. So there's a symmetrization formula which is completely obvious. You just have to write it, which says that if you f is a cocycle on gamma times d, then additive cocycle, then you have that the integral of a gamma times b of f d mu d nu. You want to express it as an integral of the same set, but with this measure. So what appears is that f times 1 minus c over 1 plus c. And the reason behind it is that, when you change when you inverse your cocycle, if you replace c by c minus 1, this just changes sign. And that will be very useful because if you apply, if you work with the integrals and you try to apply inequalities like Cauchy-Schwarz and Jensen, you want your function to be constant in the best case possible. So, and in this case, if you look at the cocycles, they take two values which are inverse of each other for a simple, the next neighbors here. So, now I just have to express the previous quantities in terms of boundaries. So, this is well known, and so let's talk about the Boltzmann boundary. So let's call it V1. V1 is simply the closure for the, I think it's the compact open topology of distance function on gamma, which are normalized to be 0 on the identity limit. Well, more formally, it means the closure of a set of functions dy, or y in gamma, of dy, which to x is shaped y minus 1x minus y minus. So when I take this closure, what I obtain is a set of points at infinity. And a point at infinity here is understood as a Boltzmann function which vanish at the origin. Okay, so by Carlson and Lebracquier, so they prove that in this very general setting that there is a stationary measure here so stationary. For which you can express the linear drift as integral quantity. So the linear drift is the following: the integral of the gamma times b of the Boltzmann function associated to a point at infinity of gamma. Psi is a point at infinity, but it's also a function, and this function is Boltzmann psi. It's also a function. So, and we're in very good position because here it's an additive cocycle. So we can hope we can try to do something with our symmetrization lemma. So we can express L to be the integral of gamma phi of the Boltzmann cocycle times 1 minus C, 1 plus C dl. I will take this formula here. Page is missing in my talk. Seriously. Seriously. Okay. So it was not my intention, but no. Yeah, I try to. Okay. For person boundary. So Poisson boundary is equipped with it's a boundary with stationary measure, and you can also Kajamanovich prove a formula for the entropy. So the entropy is simply so. Here, there is a cocycle C0. What I should write here is that the cocycle is C1. Because it's associated to B1. In fact, the entropy is equal to on gamma B0 of minus the log of the Radon-Nikodym derivative on the Poisson boundary, mu d. And we do that. And we are very happy with it because it's, again, an additive cocycle. And, but the problem is it doesn't live on the same place like this. But, however, Kamenovich and Vershik prove much more. They prove that for any boundary, you can define this quantity. It's the entropy of this boundary. And the entropy of this boundary is always less or equal to the entropy of Poisson boundary. So in fact, what you have is that H is always bigger than if you look at the Boltzmann boundary. it's bigger than log of C1 d mu 1. And then you can look at it. So you apply symmetrization formula, which says that it's minus log of C1 times 1 minus C1 over 1 plus C1 of d mu 1. Okay. So now we are ready to prove point 2 of the theorem, which will follow from very easily. So L square is certainly smaller than the integral of b square times the integral of 1 minus c1 of 1 plus c1 square d. And the fact is that the Boltzmann function is 1 Lipschitz. So you can, so this is certainly smaller than the second moment. So what we have is that L is small over n2 of mu is smaller than the integral of 1 minus c1 over 1 plus c1 squared dA. And maybe I'm missing 1/2 somewhere. Yeah. And now I will really have to take a look at my notes, because if you apply Jensen inequality for the right function here, then you get this. It's not obvious at all, and you have to look at your notes inside the function. So function is the one, so this one. So you take f of x equal to 2x reciprocal of the hyperbolic tangent times x, and you don't apply this function, you apply f of square root of x, which is increasing and convex. So, and what happens is that f of 1 minus c over 1 plus c, you get exactly what you should get, that is minus log of c1, 1 minus c1 over 1 plus c1. Okay, so if you apply this convex function and use Jensen inequality here, what you get is exactly the theorem. You get that f of L, so this is L tilde, so f of L tilde, maybe I should have maybe a mistake in the document. Should be exactly this if I didn't make a mistake. I think I have. No. Okay. So now let's turn to the second inequality. The second inequality, you have to express the spectral radius in terms of the Boltzmann cycle. So one way to see this is you consider the usual representation of pi of gamma in unitary of L2 of the boundary, the Poisson boundary this time, which is the following. You take so P of gamma applied to f. It's a function, and when you evaluate on a point, it's the usual action. But if you do it like this, it's not unitary, so you have to put the cocycle on top. And the fact is that this representation, and the fact that follows, for example, from theorems of Zimmer and Kuhn that this representation is weakly contained in regular representation. This means that if you have a spectral gap here, you have maybe not the same, but a better one here. So what I'm saying is that the norm of P of mu is smaller than rho. And it helps you because there's a thing you can compute explicitly. It's pi of mu times the constant function 1, scalar product with 1. And this is only integral over C0 1/2 the mu naught because of this formula. And this is certainly smaller because it's just a scalar product of unit vectors, certainly smaller than the rho. So then you have expressed rho, at least in terms of this one. And okay. Somehow, I hope you believe me if I say that it implies that y minus rho is smaller than integral of g 1 minus c naught over 1 plus c naught mu, where g, the function g of x, 1 minus square root of y minus c squared. Okay. And then you still want to apply, but what you want to get is a bound here that you want to see the expression of the entropy here. So you have to transform this. And the correct function to do this is to apply a function h, which is h of x. And I will take real pleasure in writing this. So, logarithm of 1 plus 2x minus x 1/2 over 1 minus 2x minus x square 1/2. And so this function is convex, increasing, and it has a property. So you can apply Jensen's equality with this function to this, and you have to compute that h proposed with g, you find the function f, which was at the beginning, and then you can conclude. Okay. Oh, and it's very high at the time. So much. Are there any questions? So maybe a word on the proof of proposition now. So what happens is that if you have equality somewhere, this implies that your cocycle, let's say C naught, takes only two values. A minus 1. And it's not clear that which group can do this, but if you take an hyperbolic group, then somewhere which is not virtually free, and there are connected components in its boundary, non-trivial ones, which correspond to the boundary of some hyperbolic subgroup. So, and if you're connected, that means that, so you can identify the Poisson boundary with the geometry boundary first. So this is the result of Ancona. And then you can say that this can't happen because you have some continuity of the cocycle and you on a connected component. And you can find a hyperbolic, so somewhere in the boundary you have this connected component. And you can find an hyperbolic element in the subgroup which has attractor here, repulsor here, and so this element may not be in our initial set of generators in the support of mu, but it means that if you express it as a word in terms of generators, then the cocycle will take only finitely many values. And moreover, you know that the action of this hyperbolic element in the group is contracting somewhere and dilating somewhere. So the cocycle cannot be, so it's smaller than one on one side and bigger than one on the other side. I won't specify which one, otherwise I might miss something. But since it takes only finitely many values, it cannot go from here to here continuously. So that implies that there is no connected component in the boundary, which means that if a group is hyperbolic, it's virtually free. Okay, I'm sorry, I didn't make the time here.
Okay, any questions? Okay, so if there are no questions, okay, and the talk by Vinogradov would be at 2:30.